Okay, I guess it's about time. So we're going to be talking to you about Protected Execution Facility, which is a new feature available in some upcoming power processors. This slide is basically to tell you that some of the concepts we presented were funded by research that was sponsored by the US and Canadian governments. Whenever we talk about it, we have to tell you that. So that you understand the security challenges. It's increasingly difficult to verify the provenance and correctness of software components like hypervisors, operating systems, and privileged software. These components provide a large attack space, and unfortunately, they can also contain a number of zero-day vulnerabilities, including zero-day attacks. And as OpenPOWER becomes more prevalent, it'll become more susceptible to this sort of stuff. So the objectives for Protected Execution Facility are to introduce this concept we call a secure virtual machine, which protects the secure virtual machine against attacks from outside the SVM components and enables the protection of the SVM code and data. We create a smaller trusted computing base, and we have an open source ecosystem associated with this. It's also integrated with trusted computing tooling, and we provide the ability to convert an existing virtual machine image running on Power into an SVM image. We don't have any limitations on the amount of memory we can protect, and any of your existing application code can run in this SVM. So a quick overview of what we're doing here. As you're familiar with Power, Power has problem state, supervisor state, and hypervisor state. We now introduce a new state called Ultravisor state. It's at the bottom because it's the highest privileged state in the machine. And this gives us the ability to provide confidentiality and integrity for SVM code and data. We're minimizing the TCP to this Ultravisor state and the hardware it's built upon. We made some processor changes, which I'll describe in a minute, and we're adding there's some firmware changes, both to host boot and Opal, and we add a whole new section of firmware called the Ultravisor. The architecture includes what's provided by the Ultravisor as well as the hardware. We've got this new mode called Ultravisor mode, which is higher privileged, as I said, and the firmware, the Ultravisor firmware, and the hardware are used to manage the security of the machine. We introduce a concept into the architecture called secure memory, which can only be accessed when you're running in secure mode by a secure VM. And we allow both a normal virtual machine and a secure virtual machine to run on the same platform. And the overhead associated with the changes is only on the secure virtual machines. So this gives you a picture, basically, starting, you can do top down or bottom up, but we'll go bottom up. You've got some storage. We have a trusted platform module. There's a private key associated with the processor that's locked in the TPM. We make some changes to implement in the hardware. One of those changes separates the memory addressable by the machine into some of its secure memory, some of its normal memory. We add this Protected Execution Ultravisor below the hypervisor, which is any hypervisor there. Linux KVM runs on top of it. And then there's a public key associated with the private key that you use this new tooling to convert a normal virtual machine into a secure virtual machine, and the secure virtual machines are stored on your standard disk. That's basically a quick overview of what we have here. So the Protected Execution term refers to the changes made to Power and OpenPOWER architecture, where each machine has a public-private key pair. They get the new firmware. We have these things we call secure virtual machines. To create a secure virtual machine, you start with a normal virtual machine and run some tooling that will also be open source and does the conversion for you. Secure virtual machines execute in secure memory, which is under the control of the Ultravisor. It's important to note that all secure virtual machines start execution as a normal virtual machine, and then they issue a new syscall. If you're familiar with the architecture, we have syscall level 1, level 2. We introduce level 3, which goes directly to this new firmware. And neither the hypervisor nor normal virtual machines can reference secure memory, and in fact, most of the hardware can't reference it. So just to talk a little bit about the format of a secure virtual machine and how the thing boots. This picture is designed if your secure virtual machine contains a Z image. So you end up with, you start off in slough, you go to grub loads the Z image, and the Z image runs, you get these new boot targets, the Z image runs, and eventually does an ultra call to move this whole thing into secure memory, and then it becomes secure. The alternative format I don't have illustrated in this picture, but it's basically to inject the ESM operand. I call it a blob here, but it's really an operand of this new ultra call. We can inject it into the initram FS, so you can have two different formats for the tooling will convert it to either one format or the other format. Either one of them is bootable, is boots by grub. The ESM operand contains these things illustrated here. The purple, the green, and the orange thing we refer to as lock boxes. What it is it's the symmetric key protecting the blue section wrapped with the public key that's associated with the hardware the SVM is authorized to run on. You can have as many lock boxes as you want. Inside the blue area is what we call the verification information. This is integrity information that's used by the new firmware to verify the integrity of the kernel, the initram FS, and the RTEST section associated with the virtual machine. There are also what we call symmetric key blobs, which are secrets that the creator of the virtual machine wants to embed in it, are also in this section. And finally, we have the passphrase for the encrypted file system. The tooling wants you to have the file system of the SVM protected by an encrypted file system. Otherwise, you can't protect it when it's at rest. So we use, like, say, decrypt can protect your disk while it's not running. So now we'll just try to walk through the changes at a little bit of a, not too quickly here, but it'll give you a base idea of what we did. We're using an address bit that's not inside the physical memory space to indicate whether the memory is secure or not. The amount of secure memory is configurable the way you normally configure machine features in Power. We added another bit or used up a previously reserved bit in the MSR to indicate that a process is actually running secure. We now have 3 bits that determine the privilege of a processor. We add the S bit to the H bit and the PR bit, which previously determined the privilege of a processor. So if you're running secure, you can be in problem state, you can be in OS state, you can be in Ultravisor state, or we have one configuration that's currently reserved. If you're a normal virtual machine, you run in problem state, privileged OS state, hypervisor state, and there's a mode 011 called problem hypervisor or adjunct mode for the hypervisor. We add a bunch of new registers, such as SMF CTRL and these others, USMOR, USRR0, USRR1, USPRG01 are similar to the registers that exist for hypervisor mode and have similar functions, but refer to when the system is running in ultravisor mode. And the U registers can only be referenced by the ultravisor, not by anyone else. We add a new instruction, URFID. The issue is that the ultravisor is the only one who can turn on the MSR sub S bit when he's returning, causing something to execute. You've probably figured out that by now that this requires a little bit of paravirtualization in the hypervisor to get it to run, and that we've done, and those changes are being upstreamed as we speak. So going at a lower level, we rely on a root of trust. And one such root of trust is a TPM, which is available in OpenPOWER systems. That's where we lock up the private key. The Ultravisor uses the TPM to get access to the symmetric key protecting the SVM. So when you do that ESM Ultra call, you pass as a pointer to us to this ESM operand I described. The Ultravisor looks in the lock boxes to see if each lock box is indexed by the number of bits from the private key, and if it sees its bits, the bits associated with its private key in there, it uses that lock box to decrypt and get the symmetric key, and then it can get the verification information and verify that the machine that you wish to become a secure virtual machine has not been tampered with. Now, before it does any of that, when you do the ESM call, what it does is it copies the non-secure machine into secure memory where nobody can touch it, and then it does all of its verification and checks. So I've told you all this. If the secure virtual machine passes the checks, then the ultravisor passes control to it with MSR sub s equals 1, and it starts running insecure. So one of the changes is that when the processor is running with that bit set to 1, it's saying that the thing running is secure, all interrupts go directly to the ultravisor, not to the hypervisor. And so, in addition, to protect the SVM, some of the resources that were previously hypervisor privileged are now ultravisor privileged, which means when the hypervisor wants to do some of its work, it's got to call the ultravisor and ask it to do the work for it. But it also allows the ultravisor to make sure that the work that's being requested won't put the secure virtual machine at risk. SVMs are protected and can only run on an authorized machine, meaning if the ultravisor machine doesn't find the symmetric key encrypted with its public key, then the request to execute will fail. And that authorization is determined by the creator of the SVM, not by the hardware platform. Okay, so unless a process is running in secure mode, it can't access secure memory. I've made that point a couple of times. Told you that you've got to use the hypervisor to use certain resources such as PTCR in the architecture. The hypervisor can only see secure memory encrypted. This feature is enforced by the ultravisor. If the hypervisor couldn't actually get access to the secure memory, it couldn't do paging for the ultravisor. The I/O system cannot address secure memory. But the SVM can request to share pages of memory with the hypervisor, which means that the SVM gets to use virtual I/O, not actual. You can't at this point dedicate devices to the SVM, but virt I/O works by using bounce buffering. The SVM can only address the memory in its page tables. It's not unlike some other trusted execution environments. When you're running secure, we do not give you access to the entire machine. We only give you access to the memory that's in your page table. And the effect of this is that not only are we protecting the SVM from the hypervisor and other normal VMs, but we're protecting the hypervisor and the normal VMs from the SVM. So you can't use this capability to build this great spyware that will nuke your machine. The ultravisor, this much significantly smaller entity, restricts the SVM to a certain set of pages, and that's all it can get to. Can't generate physical addresses and reference any arbitrary memory. The other thing about the ultravisor is it only operates in response to an interrupt. There's no timer interrupt that will cause the ultravisor to come into control. And what this means is that enabling this feature doesn't impose any additional overhead on a normal virtual machine. Any additional direct overhead, I should say. There's a small amount of overhead because the hypervisor has to use ultra calls to get to certain resources. But the frequency of the hypervisor's use of those resources is fairly low. So the overhead to a normal virtual machine is less than 2%. I don't have an exact number right now, but it's way less than that. And it would depend on, as in any measurement of overhead, it depends on the instruction mix and the frequency. The overhead mostly occurs when you're starting something up. So if you start things up and they run for a long time, you don't see it, because that's the way it works. And, there's a register called the page table control register inside the architecture, which is owned by the ultravisor. So every time the hypervisor needs to start a new virtual machine, it's got to ask to make some changes. As an overview, these resources have become ultravisor privileged. In Power, we have something called SCOM registers, which are used to configure the hardware, and those are ultravisor privileges. And sometimes the hypervisor wants to do things, but those registers control some interesting features which can allow bad things to happen. So what's going on is the ultravisor, if the hypervisor wants to do something, the ultravisor looks at the request, and if it believes the request is okay, it does it, and if it doesn't, it goes back to the hypervisor without doing the request. The processor configuration registers I just talked about, there's stop state information when you do suspend and resume. That also has to be protected so that you can't use the stop state to transition or get information out of a secure entity. I've already told you a couple of times about the PTCR and the partition table entries. We move the partition table entries into secure memory, so if you're manipulating them, you go through the Ultravisor. That's because if you could put arbitrary addresses in there as a hypervisor, you could put arbitrary addresses that could do bad things. So we also, paging for the SVM is managed by the hypervisor, but the Ultravisor manages the SVM memory. So if you think of memory as this side being normal memory and this side being secure memory, the secure virtual machine is over here on the right, and if the hypervisor wants to page it out or reduce its space, he has to say, well, I need that paged. The Ultravisor encrypts that page over here, moves it over to non-secure memory, and the hypervisor can write it out to the paging space. When it's encrypted with a technique that gives us integrity protection as well as confidentiality, and it's strong enough to give us protection against replay attacks. So the hypervisor can pick this thing up and page it back into memory, but unless it puts it back into the exact virtual address space where it was paged out from, you will get a fault and the Ultravisor will kill the SVM. So we also have to control the debug registers, CIBR, WRX, and DAWR, et cetera. And this new register, SMF-CTRL sub D, SMF-CTRL is the SMF control register. There's an E bit that says it's enabled, and there's a D bit that says that we're allowing debug facilities on secure virtual machines. When the machine turns on, it comes up it comes up with SMF-CTRL sub E off, but running in secure mode. So host boot and Opal boot in secure mode. And at some point, they will turn the S bit off. If they turn the S bit off without turning the SMF enable bit on, it can never be turned on again until the machine is rebooted. So what happens is that when you get to Opal, Opal goes to the Ultravisor. And if Opal loads the Ultravisor, it has the ability to turn that bit off or turn that bit on. So it sets the bit on, and then when it goes back to Opal so that Opal can load the base operating system, it turns the S bit off. So Opal starts its execution in secure mode and ends its execution in normal hypervisor mode, and then it goes to the booting OS. And then the only way you can get into secure mode is with an ultra call, from then on out. And so, and that's the way we do it. So I think I've just about covered all the hardware. Now, what Ram's going to do is walk you in more detail through some of the implications on the firmware.
Thanks, Guerney. Thanks, Guerney. Okay, so now Guerney has talked about the PEF, that is the Protected Execution Environment. That's a hardware feature. So that hardware feature is then being exploited by software, and finally what you get is a feature called secure virtual machines. That's something that is consumable, right? So how are we building these secure virtual machines, and what's the software architecture? I'm going to talk about that, and then I'll run through step by step as to how we boot up the system, what happens at each stages, and finally how you get this wonderful secure virtual machine. Right? So with that being said, the software architecture looks something like this. You got the host boot, the Opal boot time services, and now we got introduced a new layer called Ultravisor. Right? So you got host, let's go from host boot. That's the host boot that is, there's a little bit of changes have happened in the host boot. So it continues to do whatever responsibility it's supposed to do. Then there is the boot time services. There are some more changes here, which is supposed to initialize the environment. I'll go through those in a later slide as well, what it does. There is this new layer, which we call as the Ultravisor, which basically helps us enable the secure virtual machines. Right? And then Hypervisor is a paravirtualized hypervisor, which sits on top of the Ultravisor. This is the paravirtualization layer that we have over here, which essentially uses ultra calls to get some services, because some of the features, some of the resources which were earlier available to the hypervisor are no more available because it's a secure environment and it only can be accessed through an Ultravisor. So we have to paravirtualize the hypervisor. And then there is this layer, this small component that we have added into the hypervisor, which we call as heterogeneous memory manager. Though the Ultravisor is responsible for managing all the secure pages, the hypervisor still has to be aware of the secure pages and be able to pseudo-manage those pages with the help of the kernel. So, and that is done, the interaction with the ultravisor is done by this module over here called, which we call as UVHMM. In other words, Ultravisor Heterogeneous Memory Manager. Then we have this PRD layer, which was there earlier, which has now been broken into two pieces. There is a secure PRD and there's a PRD, and that is because the PRD is doing sensitive operations, which are privileged. Hence, as a result, we need to give some extra privileges to it. So it runs as a special kind of a secure virtual machine, and it has access to most of the resources that the Ultravisor has. So we have broken that down, and then there's a protocol between the PRD and the secure PRD. I'll not go into much detail about it, other than saying that these are broken, and some of the pieces are now in secure PRD, and some of the pieces are in the PRD. And there's a proxy layer here called the hostput runtime, which is basically acting as a proxy and interacting with the secure PRD. Other than that, there are other components within as Guerney mentioned earlier, both the secure virtual machine as well as the normal virtual machine can stay together, like run on the same machine. So we can have a normal virtual machine running, at the same time we can have a secure virtual machine running on the same platform. The changes that have happened in the secure virtual machine are like, so there are some changes in the prominent layer, which I'll talk about it at some other point in time. And then there are some small interactions that happen where we have to share the pages where Guerney mentioned about earlier. I'll talk about that later as well. So this is the high-level architecture, and these are the various pieces that I talked about. One other important aspect that we need to know is a virtual machine image by itself cannot become a secure virtual machine image. We have to do some conversion. There has to be some additional bits that has to be added, like what Guerney mentioned about, which is the ESM blob, the blob which contains the information about the integrity and the confidentiality information that needs to be provided to the Ultravisor in order for the virtual machine to turn into a secure virtual machine. So there is this tool that we have built, and will be available whenever you want to run a secure virtual machine. What this tool does at a high level is, there is this one, the first tool that we have is which we call as the ESM generator, which basically takes the kernel and the initrd, initramfs, and other information and generates some kind of a binary blob. And then we have another tool called the initramfs converter, which is basically it takes that ESM information and injects into an initRD. And then also it adds some more scripting inside the initRD to help it to mount the root file system when the virtual machine turns secure and wants to mount the root file system. At that point in time, it needs the password. That password has to be got from the Ultravisor. So for that, we need some scripts in the initramfs to do that. So we have this tool which will put those scripts into the initramfs. So that tool, along with the ESM blob generator tool, are used by this higher level tool, which we call as the image conversion tool. And what it does is it takes a normal virtual machine image, you pass it to this tool, it will generate a secure virtual machine image, right? And the main difference between normal virtual machine image and the secure virtual machine image is it has put in these ESM blobs inside each of the initRDs for the corresponding kernels. So that's the main thing it does. So you take a VM image, you provide it with all the platform keys on which all platforms do you want to run this virtual machine on, right? You provide that all those keys, it takes those keys, and you then provide it all the secrets that you want. You can, when you provide that, it will take that and finally convert into a secure virtual machine image. So this is, this along with the other changes that we talked to the different software stack will help us build and run a secure virtual machine image. So having talked abstractly about the different pieces, let me bring them all together and step by step as to what happens at what stage. So to begin with, let's see what happens. Let's say you got a brand new machine, like let's say Witherspoon or a Boston, not a Boston, a Witherspoon. So you brought it up, you powered it on. The first thing that happens is the software that gets loaded, which is the host boot which gets loaded, that gets loaded in an ultravisor mode, and it starts running. So it starts running in an ultravisor mode, and then host boot initializes the platform. It configures the memory, some part of the memory to be secure memory, which means some of the secure address spaces are now backed with memory, a separate pool of memory, and other address spaces backed by another pool of memory, which is the normal memory. It then initializes all the HDAT tables, which contains the information, which is generally the case with any other normal system as well. It then loads the host boot runtime, that piece of code it loads into memory, that is again in secure memory, and loads Opal. Opal is key boot, and then executes Opal. Right, at this point in time, host boot has loaded Opal and given control to, host boot has loaded Opal and given control to Opal, and Opal now starts running. Now, when Opal runs, what it does is the normal thing. It goes and initializes all the platform, creates the device tree by looking at the HDAT table, and then it goes and interacts with the TPM and sets up a password with the TPM. Right, and this password is needed later. I'll talk about it later, but this password is needed by the ultravisor. So he creates that password with the TPM and then loads the ultravisor. And when it loads the ultravisor, along with loading the ultravisor, it also provides the device tree and the TPM password that it just generated. It provides that to the ultravisor, right? And gives control to the ultravisor. Ultravisor gets control. What it does is it is responsible for all the secure memory that is there in the system. So it initializes secure memory. It is responsible for all the partition table and the page table. It's mostly responsible for the partition table. It initializes the partition table, then sets it up. It initializes all the data structures to manage the secure memory, the data structures to manage all the secure virtual machines, and also sets up its data structures so that it can handle any ultra calls and hyper calls that can come in the future. Right? It then synthesizes the secure PRD, which is over here. Within the secure PRD, there is this host boot runtime. It then loads actually the Opal boot time, Opal is already loaded. It it hands over the control to Opal runtime services. But at the time when it returns control to the Opal runtime services, it would have switched the mode of the CPU from ultravisor mode to a hypervisor mode, which means now onwards, the software, that is Opal software, which is getting control, cannot access any of the sensitive resources on the system. If it has to access, it has to go through an ultra call. Make sure? Is that clear? So at this point in time, ultravisor has got control, host boot runtime services has got control. Host boot runtime services then loads the hypervisor, which is normally the case, even with a normal system. The host boot runtime services loads the hypervisor, and within the hypervisor are these modules. One is the one which helps the hypervisor to be paravirtualized, and the other one is the one which helps the hypervisor to pseudo-manage the secure memory. So the hypervisor has booted, and then the hypervisor does its normal job, which is initializes its normal memory, it initializes data structures, it basically manages all the normal memory because it continues to be responsible for normal memory. And then it synthesizes a PRD and runs the host boot runtime proxy in that PRD, sets up the user space, and loads and executes the init process. So at this point in time, our hypervisor is entirely booted. A user space is running in the hypervisor. Then now comes this part where we are starting this virtual machine. So you go to the user space. At this point, you would have created a secure virtual machine image by using our tools, by taking a normal virtual machine image, running it through our tool, and would have created secure virtual machine image. You provide that to QEMU. So you provide that image to QEMU and start a QEMU. So QEMU starts, it registers its partition with the hypervisor, initializes the VirtIO devices, loads SLOF into its memory, and hands over the control to slough with the help of the hypervisor. So when the control goes back to slough, it would be running in a virtual machine mode. That is the supervisor mode in this case. So slough has got control. What slough does is it loads the prom init, the kernel, the init ramfs, and the ESM blob which is there in the init ramfs. It loads all that into its memory, and hands over control to prom init. This is where the key piece of information happens. At this point, till now, the QEMU and the virtual machine image is all backed by normal pages. So it is running in normal memory. But if at some point in time, the virtual machine has to convert to a secure virtual machine image, secure virtual machine. So at this point in time, the prom init is the one who is responsible for that. Prom init, first it initializes the data structure, but the next thing it does is it makes a U call. It calls into the ultravisor and requests the ultravisor, please switch me over to a secure virtual machine mode. So an ultra call is made, and the ultravisor takes the ESM information that is there in the blob that was there in the init RD. It takes that information, validates whether the kernel, all the software that has been loaded in its memory is all integrity protected and is the right software that needs to be run. If everything checks out, what it does is it moves all the data which is there in the normal memory to secure memory, and backs all the address space of the virtual machine image by secure memory, and hands over control back to the SVM with the SMS yes bit on, which means this secure virtual machine image can now access secure memory. So it can access secure memory, but only the memory, the pages that are there mapped into its page table, and that is done by the ultravisor. So here is a case where the virtual machine has converted from a normal virtual machine to a secure virtual machine. Right. So if you see here, all the pages here are backed by secure memory. But there's a problem if you do that, because some of the services like I/O, especially VirtIO and virtual private area, those are the areas that are needed by the hypervisor to correctly service any virtual machine. So hypervisor will not be able to service this virtual machine now onwards, because it does not have access to the VPA area and the VirtIO area, and without that, the hypervisor will not be able to do any of its operations on behalf of the secure virtual machine. So we have to make sure that some of its address space within the virtual machine can be accessed by the hypervisor. And that is done by the next step over here. The kernel, as soon as it gets control, after initializing its data structure, the first thing it does is it shares the VPA and the VirtIO area with the hypervisor using an ultra call. It calls into the ultravisor and asks the ultravisor to back those pages which were earlier backed by secure pages with normal pages. And what the ultravisor does is interacts with the hypervisor, gets some normal pages from the hypervisor, and replaces those secure pages with these normal pages. So by doing so, what happens is now the hypervisor can access some of the data that is there in the secure virtual machine image, and hence be able to service the I/O requests as well as the scheduling and those kinds of information that the hypervisor needs. It can use that to help the secure virtual machine. The hypervisor does not have access to anything else other than the areas that the secure virtual machine images kernel has explicitly shared with the hypervisor. So having done that, we have reached a stage where the pages are shared, everything looks good, and now it's a matter of mounting the init ramfs gets control, and init ramfs, as I told you earlier, it puts in some scripts inside the tools. The SVM build tools have put some scripts inside the init ramfs. Those scripts that are there in the init ramfs start executing, and one of the first thing it does is it goes and makes an ultra call to the ultravisor and asks the ultravisor for the secrets that are there in the ESM. So it takes that secret, and one of the secret is the passphrase of the root file system. So using that root file system passphrase, it is able to mount the root file system. right? So at this point in time, it bounds the root file system, and then onwards, the rest of the thing continues, and it looks as if it's a normal virtual machine, but with deep inside it, it's a secure virtual machine is running, and nobody else in the system, no hypervisor, no PRD, or nobody else can access this secure virtual machines image. It is entirely protected. The only thing that can access this secure virtual machines pages is the Ultravisor, given that the Ultravisor is a very small piece of code with a very small layer. There is hardly, it is well protected from the rest of the software which is not trusted on the system. So at this point in time, we have a running secure virtual machine. And that brings us to the last slide over here. So this is the summary. The summary is protected PEF, Protected Execution Facility, allows us to run trusted execution environment on Power and OpenPOWER systems. It enables this hardware, the CPU this feature in the CPU helps us enable secure virtual machines. Normal virtual machines can be used and can be converted to be made secure virtual machines. The entire ecosystem is open source. We will be open sourcing this Ultravisor firmware, the build tools, everything, so you can build it by yourself. It will be available in Git repository. And before we GA this system, we will make a tech preview available so that people can, the community, the open source community can try it out and help us build a more strong and a secure technology here. So with that, I'm opening up for questions.
So this requires new 2.3 CPUs?
Sorry.
Oh, sorry about that. So this new feature requires completely new revision of the CPU, DD 2.3, right?
It is DD 2.3,
Yeah.
it is Power9 DD 2.3 onwards.
Yeah. DD 2.3 is the first version of the hardware that has everything working properly. It was available in earlier versions, which we used, of course, to figure out whether it was working properly. But DD 2.3 will work.
Okay, thank you. One more question. Is it even possible to pass through PCI devices to a secure virtual machine?
PCI device pass-through is not supported at this time.
Okay, thank you.
So, sorry, did you say that this is already, will be in some Power9 generation?
Power9 processor, yes.
Yeah.
So the new registers are already in there.
The newest Power9 chip, I don't think it's for sale yet.
Yeah, okay. I just wanted to double check.
Yeah.
DD 2.3 is the chip.
That's the internal name of the chip. You know, there was DD 1.0, DD 2.0.
Yeah. Sure, okay.
So
one of the generations, good.
Sometime this year, I guess, those chips are going to start coming out in machines.
Actually, yeah,
Right,
so it's
right.
already there out there right now.
So if you have an AC 922, you have an enabled machine.
Yeah.
He probably knows the schedule better than I do.
Good,
But
thanks.
they drift into other machines eventually.
Okay.
And
So as of now, there are Witherspoons that are there with DD 2.3, so you can experiment with the Witherspoon.
well, he can't because he doesn't know how to turn it on. Yeah, so the basic point is, as he said, as the systems are due later this year, they'll have their chips on them. And when the tech preview is announced, you'll be able to get the firmware that will enable you to take one of those systems, if you already have one, and begin experimenting with this.
Okay. Another question. Is it something somehow which is already exists in the power systems with AIX, which is adopted to the OpenPOWER, or is it a completely...
Right now, PEF is in the hardware, but it is not being used by Power VM at this point in time. If you happen to have an AIX image that ran under Linux KVM, you could convert it, but it is not. It's only available. The target for this is Linux. Linux running native on the system, and the virtual machines running under Linux. Linux running under Power VM is not protected by this at this time. That's not the first. The first out target is our OpenPOWER and our Power Linux customers.
KVM hypervisor.
KVM hypervisor.
Okay. Will it require any changes in the KVM itself?
There are a few changes in KVM because it's just the hypervisor. It has to be paravirtualized, and many of those patches are already submitted and going through the community.
If you are following the community, there's a huge discussion going on in the community. We have already submitted the patches for KVM. So those are in the process of getting accepted. So the two high-level things that are needed in KVM is paravirtualized KVM, in the sense there's some set of patches which will help paravirtualize the KVM. And there's another set of patch which will help you, help the KVM to manage secure memory, pseudo-secure memory, right? So those two set of patches will enable the KVM to run a secure virtual machine.
Okay.
When we say paravirtualized KVM, what we really mean is enable KVM to manipulate the resources that were removed from its privileged. So it'll have to make ultra calls, and it's not all of KVM. It's really there's really just a small set of things that it has to now talk to us about.
Of course. So when you say that the secure memory is amount of secure memory is configurable, right?
Right.
Is it dynamic, or you?
No,
have
it's
to
not
set-
dynamically configurable. In the first release, when you get if your machine is enabled with the microcode, if you've brought up a Power machine fresh out of the box, you know the first time you boot it up, you end up booting to the petty boot menu, and you set some configuration parameters and stuff like that. And then you reboot it again, and then it comes all the way up. That's how Power works. Well, what we've done is we've added to that petty boot configuration phase where some extra menus where you say, I want PEF, or I don't want it. If I want PEF, this much of my memory I want to be secure, this much, and the rest of it is non-secure, and there's a minimum amount you have to set, and we tell you that you have to set at least this much or more to be secure.
Okay. So this thing can still be working in kind of a legacy mode without PEF?
Once the hardware runs without PEF. Otherwise, Power VM wouldn't work, and iSeries wouldn't work, all of which run on the same platform. They all run on the same hardware. They run on DD2.3 with no changes. It doesn't impact them. They're running on DD2.3 today, and DD2.3 is enabled, but what's going on is the bits off.
Okay.
All right.
Is there?
So in other words, you can take the software stack everything will look the same. Only additional thing is you'll be able to run a secure virtual machine. Everything else, if you had normal virtual machines, they'll continue to run, they'll continue to work. But if you want to run secure virtual machines, yes, you can do that.
If PEF is not enabled on the machine, there is no impact to performance whatsoever.
Okay. And what's the impact if it is enabled? The overhead?
As I said in my talk when I was talking about the hardware changes, to normal virtual machines, it's less than 2.5%. The last estimate we did was about 0.5% on startup and 0 on unsteady state. To secure virtual machines, what was our last estimate? It's less than 10%.
Okay.
And that's going to depend on what the secure virtual machine does.
Yes.
Because some things it does require more intervention by the Ultravisor, and some things it does require less. So it's going to depend on your execution mix.
One thing though is, if it is CPU bound, I don't see much performance hit. If it is IO bound, you will see some performance hit because you'll have to do some bounce buffering. Otherwise, if it is CPU bound, I don't think you'll see much of a performance impact.
Yeah, there's one other thing. In the first release, we're not enabling overcommit of SVM memory. You know, we're just not. You don't have to have overcommit for the SVM to work, so we're not enabling that. So what Ram is saying is exactly correct. If you're CPU bound, you'll see nothing. If you do a lot of I/O, that's virtual I/O through VirtIO to disk or whatever, network, whatever. That's where we have to do the bounce buffering to protect you. I didn't say it during the main presentation, but basically what happens is when an interrupt comes in, it goes to the Ultravisor. What the Ultravisor does is it takes the state of the secure virtual machine and it shoves it away. It generates some arbitrary state and sends the interrupt and reflects the interrupt to the hypervisor. If it's an asynchronous interrupt, meaning it has nothing to do with the running virtual machine, then the hypervisor gets it, examines the interrupt, does its job, and reflects it to the correct virtual machine. And eventually, however, the interrupt could have been caused by an H call, a syscall level 2 by the running secure virtual machine. That's when the secure virtual machine wants to request the hypervisor do some work for it. All of those will be reflected to the hypervisor except for get random number, for obvious reason. You cannot let something you don't trust control what you use as a random number. But what happens on a syscall level 2 is it comes into the Ultravisor like every other interrupt. The Ultravisor takes the state, shoves it away like every other interrupt, but it generates arbitrary state for the hypervisor except all of the parameters required for the syscall are passed without changing them. And it's reflected to the hypervisor, because if the hypervisor didn't get them, it couldn't do the request. And then on the way back, it passes the results into the secure virtual machine. So what we're doing is we're eliminating the side channels that can be caused that can appear because of requesting services from the hypervisor and leaving arbitrary state in all of the other registers in the power architecture that are not used for the syscall.
Okay.
Klaus, you had a question?
Hey guys, thanks for the presentation. I was curious about something I believe Guerney said. Is it possible for you to have paging between secure and non-secure memory? Is that what you meant?
Okay, yeah. So basically what we did is there's an ultra call that a secure virtual machine says that I want to have a shared page with the hypervisor. And what he's telling the Ultravisor is get some hypervisor memory and stick it in my page table at this address. What it is a secure virtual machine can reference both secure memory and normal memory, but only the memory that's in its page table. It can't reference arbitrarily normal memory. Like one of the other architectures, SGX, you know that when you're running a secure process in SGX, you have access to all of the memory in the machine. Well, we didn't do that for obvious reasons. You only get access to the memory that we let you have. That's why what we have in our architecture, we have what we call bidirectional protection. We protect the secure virtual machines from the hypervisor and normal virtual machines and other secure virtual machines. And we protect everybody from everybody. This little Ultravisor thing, which is not very large, it's not tiny, but it's not very large. It protects the hypervisor from the secure virtual machines, and it protects the normal virtual machines from the secure virtual machines because their memory is not in the address space of the SVM.
But you mentioned...
The other thing was, Klaus, you wanted to know the page in and page out, right? The paging, how it happens.
I was curious about if you have limited space in the secure memory resources, right? You need to page or swap out memory.
So, yes.
It gets encrypted by the processor itself. Is that it?
Yes. No, it doesn't get encrypted by the processor. Ultravisor does the encryption and puts it in normal memory.
Ultravisor. Okay.
Look at Hypervisor as our swap device for the secure memory. Hypervisor's memory is our swap device. Whenever we are low on memory, secure memory, we push that secure page to Hypervisor and put it in.
The page itself, when it's in secure memory, it's not encrypted, right? I mean, it's
when
only,
it's in secure memory, it's not encrypted.
Yeah,
no.
it's only a question of catching up the page faults. I mean, and allowing the secure memory to live in its own space. Right. But when you need that space for any other reason, you can swap out to normal memory and encrypt it on its way in and out. You know the latency numbers for doing this kind of thing?
We have not got those numbers yet, but to begin with, in the initial first release, I had it on one of the slides, we'll not be doing overcommit. Secure memory overcommit in the first initial release. But soon we'll be doing secure memory overcommit, which means you can have as many SVMs and there can be shortage of secure memory, in which case we'll have to page out into normal memory. But for now, since we are not allowing secure overcommit, The paging, page out is not happening, and we don't know the numbers yet.
Okay, thank
But
you.
I can tell you that what we're doing is we're doing AES IAPM, if you're familiar with cryptography. And our AES encryption algorithm uses the Power AES instruction, so you don't get much faster than that. It's really, really fast. IAPM is integrity-aware parallelizable mode. It's a mode of AES that was published about 15 years ago. It's been well checked out by the security community. Nobody's found any holes in it. What it does is it gives you your integrity protection and your encryption-decryption in parallel.
Thank you. Excellent.
I have a lot more questions, but probably the last one, because we are overcommitting time.
We can handle as many questions.
Yeah. So, is there any use in that protection facility for a host without KVM, like with a single solid operating system?
I guess what you're asking me is, can I use this if you're not running KVM? And the answer is that when you run Linux native on Power, you run the operating system in hypervisor mode. Because if you don't run the operating system in hypervisor mode, you cannot touch the facilities that are hypervisor privileged. And so that is not something that we're going to enable at this point in time, but some point down the road we probably will. It'll work.
It will work. If you have an ultravisor and if you don't want to run KVM, you can still run a KVM kernel, which is paravirtualized kernel support, because the kernel will be running in hypervisor mode. It cannot access secure facilities, right? So as a result, it will have to make ultra calls into the ultravisor. But you can run.
Yeah, the question was not can I or I can't, because I understand I can, because the KVM is Linux, is operating system. I mean, is there any use in it?
But there's a debate on that.
Like there's a protection from this kind of specter and
well, it happens.
meltdown.
It turns out that the issue is, what do you think is the future of containers in cloud infrastructure? Right now, we do a lot of containers inside of virtual machines in cloud infrastructure. But Linux itself as a native operating system, ignore what we just talked about. Linux as a native operating system supports containers natively. So you can run Linux bare metal on a Power platform with containers, with OpenStack, with all that stuff, and it works just fine. And so the debate is, what is, and we don't know, so we have to prepare for all possible futures. The debate is the future of cloud infrastructure going to always rely on virtual machines, or is it going to rely on containers? And that's the debate that's going on in the community as a whole, and that debate affects how we look at our hardware.
And to add to that, as of today, we'll support secure containers, but the secure containers will be running within secure virtual machines. And there was a talk supposed to be happening next, but due to some reason, the presenter could not come over. But finally, this thing will be exposed. The entire technology will be exposed as secure containers, and those secure containers will run within secure virtual machines. And to answer your question, yes, you probably can do secure containers on the native, but that's a debate to be had in the future.
Okay. So this reminds me of the movie with Leonardo DiCaprio, when they go to sleep, and then in the sleep they go to sleep, and then in another sleep they are going to sleep again. That Inception, yeah. That's it.
Sorry, one last question, since I believe we have the time. If you run with the Ultravisor, with the PF enabled, but you are not caring about running secure virtual machines, are you able to run an unmodified OS, or you need a modified OS on top of the, in order to boot on top of the Ultravisor?
You'll have to have a modified OS, because if the Ultravisor is there, I mean, the patches are in the kernel. They're mostly in the Linux kernel where it has to deal with paging. So it's not in some of the virtualization parts of KVM. It's all associated with the page infrastructure and with accessing SCOM registers.
Okay.
So if you reflect those patches into your OS, you're golden.
And to answer that question, add to that, there are two ways you can do that. One is disable PEF and run your normal stuff.
You wanted it enabled.
Yeah, so if you disable it, you can run it on normal stuff.
Okay.
But if you enable it, then yes, you have to
you
apply
need a
those
newer
patches.
kernel, patch kernel,
yes.
and potentially PRD. I mean, the applications need to be patched too.
Yes,
Okay.
if you enable it. But if you disable it, things are as usual.
Excellent. Thank you.
I think that should be it. Thanks a lot.
Yeah.